You know, usually when we talk about physics breaking,
It's subtle.
yeah, it's subtle, like a decimal point in the wrong place or a muon wobbling a little too much at Fermilab.
Exactly. It is usually the kind of thing where you need a PhD just to understand why everyone is panicking.
Right. But the papers you sent over for today's deep dive, this is not a wobble.
No, it isn't.
This is a car crash.
It is a complete train wreck.
Yeah.
That is really the only way to describe it.
It's a full-on collision between two of our massive observatories and, well, our entire standard understanding of the universe.
Yes. We are looking at data from the bottom of the world.
Down at IceCube in Antarctica.
Right, IceCube. And then also from the bottom of the ocean.
KM3NeT in the Mediterranean.
Exactly. And they are telling us two completely contradictory stories about the most violent objects in creation.
Primordial black holes.
Primordial black holes. It's a contradiction that simply should not exist in our current framework.
Because if you follow the standard rules of Hawking radiation.
Rules we have trusted for 50 years.
Right, rules that are practically printed on the t-shirts of every physics undergrad.
If you follow those rules, the data we are seeing is impossible. It breaks the model. Completely.
And that is our mission for this deep dive. We are trying to solve what people are calling the 100 PeV paradox.
The 100 peta-electron volt paradox.
Yeah. And we're going to look at why the physics community is currently obsessed with invisible dark charges to fix this mess.
The dark charge hypothesis. The incumbent theory.
Right, the villain of our story today, or at least the accused. But then we're going to pivot to the challengers.
And the challengers is where it gets really, really interesting. Because usually when physics breaks, people just add more particles.
Yeah, they just add more stuff to the universe to plug the holes.
Exactly. But we have two groundbreaking source papers here today that say basically stop inventing invisible particles.
Right. Contender number 1 claims we can solve this with pure classical gravity.
If we just respect the geometry.
Yeah. And the other contender claims the answer is, well, it's digital.
That space itself is a lattice.
A lattice of tokens. And that black holes are just running out of budget.
It is a battle between a smooth, curved universe and a pixelated, discrete one.
And the referee for this battle is a tiny, high-energy particle smashing into the ice.
The neutrino.
So let's unpack this for you. We need to start with the crime scene. Before we get to pixelated space or dark charges, walk me through the raw numbers.
Let's do it.
What are IceCube and KM3NeT actually seeing that has everyone so riled up?
So, to appreciate the scale here, we really need to talk about energy.
Yeah.
In particle physics, we use the electron volt as our unit.
Right.
A single photon of visible light, like the light hitting your eye right now as you listen to this, is about 2 or 3 electron volts.
Just 2 or 3?
Yeah. And a dental X-ray is maybe 50,000?
Okay, so 50,000 for an X-ray. What about the Large Hadron Collider?
The LHC.
Yeah, the biggest machine humanity has ever built.
The LHC smashes protons together at about 13 tera electron volts.
13 trillion.
13 trillion electron volts. It is an enormous amount of energy concentrated in a tiny space.
Right, so that is our baseline for big.
Exactly. Now look at the neutrinos hitting Antarctica. IceCube has been seeing these high-energy cosmic neutrinos for a while now.
And they're clocking in at around 1 peta electron volt, right?
1 PeV, which is 1,000 tera electron volts.
So a single tiny subatomic ghost particle is carrying 1,000 times more punch than the focus beams at CERN.
Exactly. And that alone is fascinating. But IceCube sees a flux of them right around that 1 PeV mark.
It's consistent.
It's high, it's significant, but it's somewhat consistent. We can model it.
But then KM3NeT turns on.
The new array in the Mediterranean.
Yes.
It starts staring into the abyss and it catches something terrifying.
The anomaly.
They're reporting events pushing up toward 100 PeV.
Okay, so we have 1 PeV events in the ice and 100 PeV events in the water.
Yes.
Why is that a crisis? I mean, nature makes things of different sizes all the time. I can find a pebble and a massive boulder on the exact same beach. Why can't we just have both neutrino energies floating around?
Because of where we think they come from.
The source.
Right. The leading suspect for these ultra-high energy neutrinos isn't a supernova or a quasar, it's primordial black holes, PBHs.
And these aren't standard black holes.
No, these aren't the stellar monsters formed from dying stars. These are tiny, ancient black holes.
Formed right after the Big Bang.
Seconds after. Maybe the size of a proton, but with the mass of an asteroid.
Wow.
And they are evaporating.
Okay, this is Stephen Hawking's famous discovery. Hawking radiation.
Exactly. And Hawking radiation is a thermal process. It is strictly determined by temperature.
So it follows thermal rules.
Right. As a black hole gets smaller, it gets hotter. And as it gets hotter, it spews out more energetic particles.
Okay, I follow.
If you have a black hole hot enough to spit out a 100 PeV neutrino, it implies a very specific, incredibly high temperature.
I see where you're going. If the stove is hot enough to burn a hole in the pan, it should also be boiling the water.
Better yet, think of it like a dimmer switch on a light bulb.
Okay, a dimmer switch.
You turn it up. First it glows red, then yellow, then white.
Right.
If you see blue light, which is the high energy end, you know that bulb is also emitting all the colors below it.
The red, the yellow, the green.
Exactly. It doesn't just skip to blue. Physics does not like jumps like that in thermal systems.
So if KM3NeT sees 100 PeV, which is the blue light in this analogy, the black hole must be emitting a massive amount of 1 PeV red light along with it.
Precisely. The math of the Schwarzschild model, the standard black hole model, is totally rigid here.
It treats all particles roughly the same based on that temperature.
Yes, if you produce 100 PeV particles, you must be producing a catastrophic flood of 1 PeV particles.
And an even bigger flood of gamma rays.
Exactly. And that is the smoking gun.
That's the problem. We see the 100 PeV spike.
But we don't see the flood of lower energy gamma rays that should accompany it.
The sky should just be glowing with gamma radiation if these black holes exist and are evaporating like that.
But it's dark. We are seeing the blue light without the red.
It's like seeing the penthouse of a skyscraper floating in the air without the 50 floors beneath it.
That is a fantastic analogy. Standard physics says you cannot have the penthouse without the building.
And yet, the detectors are seeing the penthouse.
Right.
So physics is broken. The standard model predicts a gamma ray catastrophe that isn't actually happening.
Not in our observations, no.
How has the scientific establishment tried to patch this hole? Because I know they didn't just throw up their hands and quit.
No, they did what particle physicists always do when the data doesn't fit.
They invented a new particle.
Or rather, a whole new sector of reality. This is the dark charge hypothesis.
Okay, this is the villain of our story today, or at least the incumbent theory that our two source papers are trying to dethrone.
It's the current favorite because it works mathematically.
What's the idea?
The idea is this. What if the black hole isn't just a standard Schwarzschild object? What if it carries a charge?
Like an electric charge.
Similar, but not electromagnetic.
Why not just electric?
Because if it were an electric charge, the black hole would just neutralize itself by sucking in oppositely charged particles from space.
Oh, right. A positive black hole just eats nearby electrons.
Exactly. It would short circuit almost immediately. So this has to be a charge that cannot be neutralized by normal matter.
A dark charge.
Specifically, a dark U1 charge.
Okay, hold on. You can't just say dark charge and expect me to buy it. What does adding a dark charge actually do to the black hole?
Fair question.
How does it fix the penthouse problem?
It acts as a brake pedal.
A brake pedal.
Yes. In general relativity, if a black hole has a charge or a spin, it has an extremal limit.
An extremal limit.
There's a point where the repulsive force of the charge fights against the gravity that's trying to crush it.
So the charge pushes out and gravity pulls in.
Right. As the black hole evaporates and gets smaller, this dark charge becomes more and more concentrated.
So the repulsion gets stronger.
Yes. It stops the black hole from getting infinitely hot. It keeps it quasi-extremal.
It caps the temperature.
It caps the temperature. But here is the trick. The theory argues that this specific dark interaction selectively suppresses the emission of the standard particles,
The gamma rays and the low energy debris.
while allowing the high energy neutrinos to escape through a specific decay channel in the dark sector.
That sounds incredibly engineered.
It is.
It's like saying, we have a problem with gamma rays. Okay, let's just invent a force that specifically shuts off gamma rays.
It is entirely engineered.
Yeah.
That's the main criticism of it. To make this work, look at what you have to add to the universe.
What's the bill?
You need a dark gauge boson.
The carrier of this new force.
Right, a dark photon. You also need a dark fermion to actually hold the charge.
Okay.
You need a new conservation law to ensure the charge doesn't vanish.
It just keeps adding up.
You essentially have to double the complexity of the standard model.
It's bloatware.
It is theoretical bloat.
It's like downloading a 50-gigabyte software patch just to fix a single typo in a text file.
Scientists call it a severe violation of Occam's razor.
The idea that the simplest explanation is usually the best one.
Right. It multiplies entities beyond necessity.
But,
And this is important, it fits the data.
of course it does. It was built to.
If you tune the parameters just right, You get the 100 PeV neutrinos, and you completely kill the gamma rays.
So it works, but it's ugly.
It works, but it implies that our visible universe is just half the picture.
A shadow universe.
Basically says the math isn't wrong, we just can't see the other half of the variables.
And that brings us to the challengers. We have 2 papers on the desk that looked at this shadow universe explanation and said, no thanks.
They both want to solve the problem without adding a single new particle.
Let's start with source A. The paper is titled, Energy Selective Neutrino Emission from Near-Extremal Compact Objects Without Additional Gauge Structure.
Very catchy title.
It rails right off the tongue. But this is the classical purist approach.
Yes.
These authors are basically saying we have been doing gravity wrong, or at least we've been oversimplifying it.
Exactly. Source A argues that we have underestimated the sheer power and complexity of standard gravity. They focus on a concept called gray body factors.
Gray body factors, honestly, this sounds like an alien species from a sci-fi show.
The gray bodies are coming.
Right. But what is it really?
It's actually a term from thermodynamics. In physics, a black body is a perfect absorber and emitter. It radiates perfectly according to its temperature.
Okay, the ideal scenario.
But real objects are gray bodies. They aren't perfect. They filter things.
They filter.
Source A argues that a black hole, especially one that is spinning incredibly fast, acts as a filter. It is not just an open door for particles to leave.
It's an obstacle course.
It's a massive obstacle course.
So the black hole basically has a bouncer at the door.
In a way, yes. And the bouncer is the curvature of space-time itself. We have to introduce the Kerr-Newman metric here.
The Kerr-Newman metric. Let's break that down.
That is the mathematical solution for a spinning charged black hole.
Okay.
When a black hole spins near the speed of light, it literally drags space along with it. This is called frame dragging.
Frame dragging, like when you're on one of those spinning rides at the carnival.
A gravitron.
Yeah, the gravitron. And the floor drops out, but you are stuck to the wall. You can't even lift your head up because the rotation is pinning you.
That is a very apt analogy. The space itself is rotating. Now imagine a particle trying to escape the event horizon.
It wants to get out.
To get out, it has to tunnel through this intense, swirling angular momentum barrier.
That sounds difficult.
It is. Source A ran the numbers, the actual quantum field theory calculations in curved space, and they found that this barrier is highly sensitive.
Sensitive to what?
To energy. It acts as a high-pass filter.
Okay, lay that out for me. A high-pass filter.
It means high-frequency, high-energy signals can get through, but low-energy signals get blocked.
Blocked by the spin.
The paper demonstrates that low-energy particles, like those 1 PeV neutrinos we saw at IceCube, and crucially, the gamma rays, they have a very hard time punching through this rotational barrier.
What happens to them?
They get reflected back into the hole.
They bounce off the bouncer?
Effectively, yes.
Yeah.
But the high-energy particles, the 100 PeV monsters seen by KM3NeT, they have enough momentum to pierce the barrier.
They tunnel out successfully?
Yes.
Wait, so the gap between 1 PeV and 100 PeV isn't because of some dark charge magic at all?
Not according to Source A.
It's just aerodynamics. Or I guess gravidynamics.
Gravidynamics is a perfect word for it. It is a geometric filter. Think of it like a radio signal trying to get through a tunnel.
Okay, driving through a mountain?
Low frequencies might get blocked by the tunnel walls entirely, but high frequencies pass right through and reach your radio.
So the black hole is naturally suppressing the lower energies.
Simply by spinning.
And the gamma rays. The whole reason the dark charge was invented was to hide those gamma rays.
That is the beauty of it. Gamma rays, generally speaking, are in that lower to medium energy bracket relative to these ultra-high energy neutrinos.
So they get trapped.
If the filter blocks the 1 PeV neutrinos, it also blocks the gamma rays.
So the gamma ray problem literally solves itself.
Yes, you do not need a dark charge to suppress the gamma rays. The spinning geometry of space-time does it for you.
That's incredible.
The paper states it clearly. Quote, energy selective suppression arises generically from near-extremal horizon physics.
Generically. That's scientists speak for. It happens naturally. You don't have to force it.
Correct. They argue that as the black hole gets near-extremal, meaning it's spinning so fast it's almost ripping itself apart, the temperature drops, and this filter effect becomes the dominant force.
The 100 PeV neutrinos are the only ones with the VIP pass to get out.
Exactly.
That is elegant. I mean, it uses the tools we already have, Einstein and quantum field theory.
It is a conceptually economical solution.
But it's heavy on the math. And it makes a major assumption, right? It assumes space is smooth, continuous, curved.
Yes. It assumes the fabric of space-time is real.
Which brings us to the challenger that completely flips the table. Contender number 2. Source B.
The digital universe.
This paper is wild. The title alone, Token-Saturated Twist-Tech Filtering. I feel like I need a glossary just for the title.
It is definitely the disruptor in this debate. Source B comes from a completely different framework than anything we've discussed so far.
Lay it on me.
It argues that the universe isn't continuous. It is discrete. It's pixelated.
Like a video game. Or a JPEG.
In a sense, yes. The theory posits that space-time is a lattice. Specifically, a tetrahedral grid.
A grid?
And black holes aren't just gravity wells. They are information processors.
Processors.
And they operate on a budget.
A budget, like they have a spending limit.
Literally. The paper calls it the token saturation model. It introduces a variable, phi sub h, which represents the flux or token budget of the event horizon.
Okay, a token budget.
In this model, evaporation isn't just heat radiating away into the void. It is the active conversion of spatial geometry into time.
Okay, that is heady. Converting space into time.
Think of it as processing information. To emit a particle, the black hole has to pay for it using its token budget.
Pay for it.
It has to physically reconfigure the lattice to make that particle exist outside the horizon.
So the black hole has a wallet full of tokens, and every single time it wants to spit out a neutrino, it has to pay.
Yes. And this is where it gets really interesting, and where it completely diverges from everything you probably know about physics.
Okay.
The cost depends on the complexity of the particle.
Complexity.
In this model, a neutrino isn't a point. It's a geometric shape, a twist loop on the lattice.
A twist loop, like a knot.
Exactly like a knot. Imagine a neutrino is a specific knot tied on this three-dimensional tetrahedral grid.
Okay, I have that image.
To emit that knot, the black hole has to perform rotations on the grid. The paper defines a cost for this called inversion stall.
Inversion stall.
Think of it as the processing cost or the energy tax to create that specific geometry.
The computing power required.
Now, here's the counterintuitive part. You might think low energy means cheap.
Sure. In our normal world, a small AA battery is cheaper than a massive car battery.
Right. Low energy should be easy to make.
Easy to process.
But in twist-tech geometry, it is the exact opposite. Low energy corresponds to a small k value.
Small k.
In lattice math, a small k means the loop is tight, complex, and has many unpaid rotations.
It's a messy knot.
It is an incredibly messy, tight, convoluted little knot. To process that knot, to untie it from the black hole and release it into the universe, requires a massive amount of stall tokens.
Because it takes so many operations to unravel.
Exactly. It is highly expensive to process.
So low energy equals expensive.
Yes. Low energy is high complexity.
And high energy, the 100 PeV ones?
High energy corresponds to a large K. On the lattice, a large K represents a smoother, broader, simpler loop.
So it's not a messy knot.
No. It requires very few localized rotations to generate. Its stall cost is incredibly low.
That turns everything on its head. A high-energy neutrino, the 100 PeV monster, is actually cheap for the black hole to produce.
Exactly. It's a bargain.
Wow.
So now look at the black hole. It's evaporating, it's shrinking, it's getting near extremal.
Right.
In the token model, this means its wallet, that phi sub h, is emptying out. It is running out of tokens.
It's broke.
It's broke.
Now, it looks at the menu of particles it wants to emit. Okay. The 1 PeV neutrino, the low-energy one, costs 1 million tokens because it's a complex knot.
And the black hole says, I can't afford that.
It rejects it. The transaction stalls.
Card declined.
But then it looks at the 100 PeV neutrino. It's high energy, but geometrically simple. It only costs 10 tokens.
And the black hole says, I can afford that.
It emits it.
That is bizarrely logical. It's like a vending machine that rejects pennies because the sorting mechanism is too worn out to count them, but it still takes dollar bills perfectly fine. That is a surprisingly accurate analogy. The mechanism of the horizon is saturated. It can only handle highly efficient transactions.
Which are the high-energy, large K particles.
Yes. And notice, it achieves the exact same result as source A. It suppresses the low energy and lets out the high energy.
The same exact outcome.
But the mechanism's totally different. Source A is a physical wall. Source B is a transaction failure.
And just to confirm, this solves the gamma ray problem too.
Yes. Gamma rays would also be low, high complexity knots in this framework.
So they're expensive.
Their stall costs would be astronomical compared to the shrinking budget of the black hole. They simply cannot be processed.
So we have a three-way cage match here.
We do.
In one corner, the dark charge. Bloated, full of new invisible particles, but easy to calculate if you just add enough variables.
Right.
In the second corner, the classical purist. using strict Einstein gravity to build a geometric wall.
The gray body filter.
And in the third corner, the digital token model, using a cosmic budget to reject geometrically expensive particles.
And we have to ask ourselves, how do we choose?
This is the heart of the scientific method right here.
It is. It's not just about fitting the curve to the data, it's about how you fit it. What underlying reality does your model imply?
Let's talk about Occam's razor again. We mentioned it hates the dark charge.
Occam's razor asks us to minimize entities. Do not invent things if you don't have to.
And the dark charge model adds 4 new entities to reality.
At least 4. It assumes a whole mirror universe essentially exists just to fix this one math problem with black holes. It's conceptually expensive.
Whereas source A adds 0 entities.
0. It relies entirely on the standard model of particle physics and general relativity.
It just says you guys were doing the math wrong by ignoring the spin barrier.
Exactly. It scores very high on conceptual economy.
But source B is tricky. It doesn't add particles, but it completely changes the board.
Source B relies on what we call structural unification. It asks us to accept a huge premise that space is a lattice.
That's a huge pill to swallow.
It is. But look at the payoff. Source B claims to solve 2 monumental problems at once, not just the neutrino gap.
What else does it solve?
The black hole information paradox.
Oh, right, the famous paradox. If a black hole completely evaporates, where does all the information of the stuff that fell into it go?
Exactly. Hawking struggled with this for decades.
Because if a book falls into a black hole, and the black hole disappears, did the information in the book disappear from the universe?
Quantum mechanics says no, information is strictly conserved. Gravity says yes, it's gone.
And source B fixes this?
Source B's token saturation mechanism was originally designed specifically to save information.
Wait, really?
Yes. The tokens are the information. The budget ensures that the cosmic books balance when a black hole dies.
So it preserves the data.
The authors of Source B are essentially saying, hey, this same token mechanism that saves quantum information also happens to perfectly filter these high-energy neutrinos.
That is a massive 2-for-1 deal.
It is. Source A is like a specialist surgeon, fixing the neutrino problem very cleanly. Source B is a general practitioner claiming to heal the whole patient unifying gravity and quantum mechanics together.
Unifying the neutrino tension with the information paradox?
Yes.
That makes it incredibly tempting. But we can't just vote on which one sounds coolest. This is physics. We need proof.
Me too.
How do we tell who is actually right? Is there a test?
There's an observational battleground coming up. We need to look at the flavor ratios.
Flavor ratios. Neutrinos come in flavors, right? Electron, muon, tau.
Correct. Now, the dark charge model, because it's just a simple brake pedal on the whole system, predicts that the neutrinos coming out should be in a standard mix.
So roughly 1 to 1 to 1.
Exactly. Or if they interact heavily with the dark sector, they might have a constant flat distortion.
Vanilla, chocolate, strawberry, all equal. Boring.
But Source A and Source B predict something dynamic. They predict flavor drift.
Drift, meaning it changes.
As the energy changes, the flavor mix changes. For Source A, the classical purist, the gravitational barrier works slightly differently for different particles depending on their subtle mass differences.
Because they have slightly different properties.
Yes. So at 1 PeV, you might see mostly muons getting through, but as you move up to 100 PeV, the ratio shifts smoothly to TOSs. It is a continuous curve.
A smooth curve. That is the signature of the analog universe.
Exactly. Physics in a continuous universe is smooth. But Source B, the digital token model, predicts something sharper.
Because it's on a grid.
Because it's based on a lattice, physics happens in discrete steps. It predicts energy-dependent flavor drift tied to what they call the inversion floor.
The inversion floor. That sounds like a breakdancing move.
It means we might not see a smooth curve at all. We might see sharp steps or jumps in the flavor ratio.
Like stairs.
Like stairs. At a certain exact energy level, the black hole suddenly has just enough tokens to buy a different flavor, and the ratio snaps to a completely new value.
So if we look at the data from the detectors in, say, 10 years,
right,
constant ratio means dark charge wins. Smooth curve means Einstein and Source A win. Step jumps mean the matrix Source B wins.
That is a very provocative way to put it, but yes. That is the test. If future detectors see a staircase pattern in the neutrino energy spectrum, it is incredibly strong evidence for the digital nature of space.
And there's another test, right? Something involving the dark sector.
Yes, dark radiation.
If the dark charge model is true, we should be able to see something.
The dark charge model requires the black hole to emit dark photons to balance out the energy. Eventually, we might build detectors sensitive enough to see this missing energy, or these dark discharges.
But source A and source B say.
They both emphatically say no. There is no dark radiation.
None at all.
What you see is what you get. If we account for all the standard gravity and all the standard neutrinos and the energy balance is absolutely perfect, then the dark charge theory is dead.
I love that. It is a clear-cut prediction. It's falsifiable.
Science loves falsifiability. It's the only way forward.
Okay, let's zoom out for a second. We have been deep in the weeds of gray body factors and Hecke tokens. But what does this mean for the listener driving to work right now?
The big picture.
Yeah. Why should they care if a primordial black hole pays with digital tokens or just has a gravitational bouncer?
It matters because these theories represent three profoundly different visions of our place in the universe.
Break that down for us.
If the dark charge theory is right, we live in a shadow universe.
Okay.
It implies that for every particle we see, every atom in your body, every star in the night sky, there are complex, invisible structures all around us that we can never touch, only infer.
It makes our reality feel crowded.
Haunted, even. We are surrounded by ghosts.
Like we're sharing a room with invisible roommates who keep moving the furniture, but we never see them.
Yes. But if Source A is right, it is a massive victory for human intellect.
Because we didn't need the ghosts.
It means Einstein was right all along. It means the universe is knowable, smooth, and actually follows the rules we wrote down 100 years ago.
We just needed to be smarter about the math.
Exactly. It's a comforting, conservative victory. The classical world holds.
Keep calm and carry on calculating.
But if Source B is right, that is the paradigm shift.
The digital universe.
If Source B is right, space isn't empty. It is a computer. It is a data structure.
Reality is rendered.
It means that at the smallest conceivable level, reality is made of bits or tokens. Neutrinos aren't just dust flying through a void. They are lines of code executing in the lattice.
That keeps me up at night. The idea that we could look at a black hole, an object trillions of miles away, and literally see the pixels of the universe.
It moves physics from discovering nature to decoding the software.
It connects right back to the conceptual economy we discussed earlier.
Right. Scientists generally prefer Source A because it's safe, doesn't break the world, it just fixes the math.
The Source B is radical.
It demands we rethink absolutely everything: space, time, matter, information. But sometimes the radical answer is the only one that truly fits the data.
And the fact that Source B unifies the neutrino problem with the information paradox, that is a ridiculously strong selling point.
It's like finding a single key that miraculously opens two entirely different locks.
Structural unification is a powerful lure for theorists. When one mechanism explains two seemingly unrelated mysteries, it really feels like truth.
It feels like you stumble onto a fundamental law of nature.
So, to summarize the cage match for you all, we have the bloated theory, the dark charge.
We have the classic fix, the gray body factors.
And we have the pixelated fix, token saturation.
And right now, the data from the ice in Antarctica and the water in the Mediterranean is just sitting there, waiting for us to decide.
The neutrinos are hitting the sensors regardless of our theories. They don't care what we think.
It is amazing to think that buried in that ice is the definitive answer to whether we live in a smooth curve or a pixelated grid.
It reminds us that empty space is actually the most complex thing in the entire universe. We used to think space was just a stage where the actors performed.
Now we know the stage itself is acting. It is participating.
Here is a final thought for you to chew on today. We spend so much time in physics looking for dark matter and dark energy, inventing these invisible monsters to explain the gaps in our understanding.
We do. We love adding entities.
But what if there are no monsters? What if the gap is just geometry? What if we are just looking at a profoundly complex pattern and calling it a ghost because we haven't figured out the pattern yet?
Are we too quick to invent ghosts when geometry does the job perfectly well? That is the question of the century.
If you want to dive even deeper into this, go look up twist-tech lattice or Kerr-Newman geometry. But be warned, it is a rabbit hole you might not come back from.
Indeed, it is a one-way trip into the foundation of reality.
That's it for this deep dive. Thanks for listening to us unpack the universe.
Until next time.
Stay curious.